Morning everyone. So, we are starting with this in this class some of the problems that whatever we have solved in the last class. You are just looking into some of the examples. In the last class we have looked into an example of osmotic pressure controlled ultrafiltration, one gel layer controlled ultrafiltration and another batch gel layer controlled ultrafiltration problem. Now, in today's class we will do a problem, we will start with a problem which requires the not a constant boundary layer thickness or film theory. We will be utilizing the two dimensional model for developing concentration boundary layer and how to utilize those equations to get a better accurate prediction of permeate flux or permeate concentration. So, this problem number 4, it deals with the ultrafiltration of a macromolecular solutes solute. It has a diffusivity of 6 into 10 to the power minus 11 and the solution is flowing through a rectangular channel of length 1 meter, width 5 centimeter, okay, and half height of the channel, that is h is 1 millimeter. So, that is 10 to the power minus 3 meter and the flow rate, cross flow rate is 40 liter per hour and transmembrane pressure drop delta P is 500 kilopascal. Membrane permeability is given as 2.5 into 10 to the power minus 11 Newton second per meter cube. The feed concentration C naught is 10 kg per meter cube. The real retention is given as 1, okay, and membrane is placed at the bottom only. At the bottom of the channel, that means only one single wall, and pi expression with concentration is given as 1.5 into 10 to the power 4 times C, where pi is in Pascal and C is in kg per meter cube. Okay. So, this is the problem. We have to find out what is the permeate flux. So, basically our aim is to find what is the permeate flux of this process. This is a steady state process, but in this case we are not saying that it is a constant boundary layer thickness or film theory will be applicable. It will be utilizing the method that we have derived for the developing mass transfer boundary layer or two dimensional analysis. But what we will be doing here, we will not be solving any of the differential equations, we will be taking the expression of Sherwood number relationship and the average Sherwood number relationship in terms of average permeate flux and the shortcut method that whatever we have developed earlier, discussed earlier. So, it is a we will be using that method. So, that method will be more accurate than the film theory method, and you will be basically in this problem we are trying to filter the solution of a protein solution which will be having a diffusivity of 6 into 10 to the minus 11 flowing through a rectangular channel with a cross flow rate 40 liter per hour. The dimension of the various dimensions of the channel are given, and operating pressure, transmembrane pressure drop is also given, the membrane permeability is also given, feed concentration is given, real retention is known and that is 1, and the relationship of osmotic pressure as a function of concentration unknown. So, we would like to find out what is at the steady state, what is the value of permeate flux. So, let us look into the solution to this problem. First, you calculate the area, since the flow rate you would like to require to find out the cross flow velocity, right, in order to calculate the Reynolds number and in order to calculate the mass transfer coefficient. So, therefore, you have and the flow rate is given, you should know the area of cross section of the channel. The area of cross section is 2 WH Okay, this h is the half height. So, 2h is the total height, w is the width, and this turns out to be 2 into 0.05 into 10 to the power minus 3 meter square. This turns out to be 10 to the power minus 4 meter square. Okay. The Q is the flow rate, that is 40 liter per hour. If you convert the flow rate into meter cube per second, it turns out to be 1.11 into 10 to the power minus 5 meter cube per second. So, if you divide the flow rate by the cross sectional area, you will be getting the length averaged, the area averaged the cross flow velocity. This will be 1.11 into 10 to the power minus 5 divided by 10 to the power minus 4. So, this will be 0.11 meter per second is the cross flow velocity. Now, the Reynolds number will be defined on the equivalent diameter. Okay. So, you should calculate the equivalent diameter. The equivalent diameter is d equivalent equal to 4 into half height, and this turns out to be 4 into 10 to the power minus 3 meter, 4 millimeter. You should calculate the Reynolds Smith d by L, and it turns out to be 2.93 into 10 to the power 4. Okay, I am not doing this in detail. So, you can calculate the, just put the numbers and get the relationship, get the value. Okay. So, these will be required to calculate the Sherwood number. The osmotic pressure difference, delta pi is 1.5 into 10 to the power 4 cm minus Cp. It is basically pi at the membrane surface minus pi at the permeate stream. So, since pi is given as a linear function of concentration, so this will be 1.5 into 10 to the power 4 cm minus Cp. Since your Cp will be equal to 0, since Rr is equal to 1, that means your permeate concentration will be equal to 0. So, delta pi will be nothing but 1.5 into 10 to the power 4 times cm, right. So, you can make it non-dimensional, that means you multiply and divide by C naught. So, this will be cm by C naught, and this will be nothing but cm star. So, if you put the value of C naught, I think that will be 10 to the power, that will be 10 kg per meter cube. So, delta pi will be 1.5 into 10 to the power 5 cm star, where cm star is nothing but the non-dimensional concentration on the membrane surface. So, let us look into the value of delta pi by delta p. Okay. The osmotic pressure difference will be 1.5 into 10 to the power 5 cm star, and what is delta p? The transmembrane pressure drop, it is 5 into 10 to the 5. So, it will be 0.3 times cm star. Okay. So, depending on the value of cm star, let us say cm star will be about 5 times, 4 times. Okay. So, delta pi will be around 1.5, if it is 5 times, it will be 0.15. So, it will be 15% of the total transmembrane pressure drop. So, that is considered to be more or less significant. Okay. So, now we will be utilizing the method of the shortcut method for the 2-dimensional analysis, that whatever we have discussed earlier. So, that means the analysis we are going to adopt in this particular problem is not the film theory. Okay. It is basically developing mass transfer boundary layer, and we will be utilizing the method of shortcut method that we have discussed earlier in terms of length average Sherwood number. Okay. So, we can find out what is the Darcy's law, the solvent flux using Darcy's law, the non-dimensional solvent flux, that is PEW, is nothing but J d by d. This is equal to, if you remember, 1 B1 minus into 1 minus delta pi by delta p, where B1 is a parameter, it is a non-dimensional parameter. If you remember, it is LP times del p d equivalent divided by diffusivity. If you put the values, you can get an idea what is this non-dimensional number. The LP was 2.5 into 10 to the power minus 11, delta p is 5 into 10 to the power 5 Pascal, the equivalent diameter will be 4 into 10 to the power minus 3 and diffusivity will be 6 into 10 to the minus 11, and it turns out to be in the order of 833.33. So, the value, the parameter, non-dimensional parameter B1 for the case of ultrafiltration will be always in the order of 1000. Okay. So, you can have PW is equal to 833.33 into 1 minus 0.3 cm star. Okay. And if you remember, if you look into the derivation of the shortcut method earlier, we have seen that this is a length average permeate flux, right. If this Cm star is the length average concentration on the membrane surface, the lambda 1 we have defined as Pw divided by Reynolds Smith d by L raised to the power 1 upon 3, and if you put the value expression of this Pw here, then lambda 1 turns out to be 833.33 into 1 minus 0.3 cm star divided by this we have already obtained 2.93 into 10 to the power 4 raised to the power 1 upon 3. Okay. Now, you can rearrange this expression can express Cm star in terms of lambda 1. If you really do that, that means you just rearrange from this equation, you can get Cm star is equal to 3.33 minus 0.123 lambda 1. Okay. Now, in terms of mass transfer coefficient, and length averaged Sherwood number, you please look into your notes and look into the relevant expression during when we derived those relations here in this class. So, lambda 1 was Pw bar divided by Reynolds Smith d by L raised to the power 1 upon 3 will be is equal to 1.85 into 1 plus 0.32 lambda 1 plus 0.02 lambda 1 square minus 8.05 into 10 to the power minus 4 lambda 1 cube, okay, 1 minus 1 over Cm star. This comes Pw is equal to 1.85 Reynolds Smith d by L raised to the power 1 upon 3, this is k times 1 minus 1 by Cm star. I think that these we have derived in the class earlier. Okay. So, this equation, so you will be getting two equations. Those two equations have to be solved with the two unknowns. The unknowns are, so two equations and two unknowns, that will be Pw bar and Cm star. So, I am going to put Pw bar. So, you had one equation that relates Pw bar and Cm star, that is this equation. Okay. The another equation is Pw bar and lambda 1 we have already found out, lambda 1 can be expressed in terms of Cm star earlier, that we are going to substitute here, that will constitute a new equation. So, we will be getting two equations, two unknown system, and these two are algebraic equations. Okay. So, we are going to do that. So, you have to solve it by iterative technique. Solution maybe Newton-Raphson. Okay. Now, your Cm star, so with the Newton-Raphson or any iterative solution, you should guess the first you guess the value of Cm star. So, guess Cm star, and what is the judicial guess of Cm star? The minimum value of Cm star will be 1. So, Cm star has to be greater than 1, but you should know that. But what about lambda? what about lambda 1? Now, you can get an upper limit of lambda 1 because Cm star is equal to 3.33 minus 0.123 lambda 1, and the condition Cm star is always greater than 1, that will give you a lambda 1 which is always less than 18.94. Okay. Right. So, this will give a bound on lambda 1, what are the different values of lambda 1 that we are going to select. Now, if you combine, so we identified two equations and two unknown. If we combine the two equations can be combined in one equation in terms of lambda 1. Okay. What is that equation? Lambda 1 is equal to 1.85 into 1 plus 0.32 lambda 1 plus 0.02 lambda 1 square minus 8.05 into 10 to the minus 4 lambda 1 cube into 1 minus 1 divided by 3.33 minus 1.123 lambda 1. So, it is 1 minus 1 by Cm star. So, Cm star can be expressed in terms of lambda 1. So, this equation has to be solved in order to get the value of lambda 1. Once you get the value of lambda 1, you can get the value of Cm star. Once you get the value of Cm star, you can get the value of permeate flux. So, this equation can be solved again using iterative technique. Either you combine these two equations in terms of Cm star, or you cast these two equations in terms of lambda 1. Okay. So, in this particular case we have cast in terms of lambda 1. Now, for different values of lambda 1, so you select a value of lambda 1, evaluate the right hand side and check whether the right hand side is coming close to the assumed value or not. That is the idea. So, lambda 1 and right hand side of this above equation, if you select 2, this comes out to be 2.14. If you select 2.14, it is 2.21. Okay. This is, if it is 2.21, it is 2.24. If you select 2.24, then it will be 2.25. Okay. So, this is called a successive substitution technique. Okay. You guess a value of lambda 1 and just put it there, and the converged value will be the next case and see. So, the converged value will be around 2.24. Okay. So, if we select that, then you can calculate what is the length averaged permeate flux. It turns out to be 69.05, and if you put J bar d by d is equal to P W bar, the length averaged permeate flux becomes 1.04 into 10 to the power minus 6 meter cube per meter square second. Okay. That is the value of length averaged permeate flux. So, you can calculate what is the permeate flux, what is the membrane surface concentration. So, membrane surface concentration turns out to be 3.05 Cm star. So, Cm is 30.5 kg per meter cube. We have seen that for this particular problem, the membrane surface concentration, average length averaged membrane surface concentration is 3 times the feed concentration. Okay. And the mass transfer coefficient you can calculate, that is Sherwood number, length average, it turns out to be 103 for this particular problem, and just put the definition of the mass transfer Sherwood number in terms of mass transfer coefficient and diffusivity, equivalent diameter, etc. The average length average mass transfer coefficient turns out to be 1.55 into 10 to the power minus 6 meter per second. So, this problem gives a demonstration how we are going to use a more accurate method that we have discussed earlier, that is a 2-dimensional approach in terms of length average Sherwood number and length average permeate flux and all the length average membrane surface concentration, all these quantities are the length averaged. So, in this process also, although we have used 2-dimensional model, we are not solving any differential equations or any ordinary differential equations or partial differential equations. Our equations will be basically boiling down in the solution of 2 simultaneous algebraic equation, okay, exactly like the film theory equations, but the only formulation is changed. Now, you can use this data and use the film theory model and get the prediction and see what is the value of permeate flux you are going to get, and it is expected using film theory you are going to get a permeate flux which will be less than the flux that we have calculated by this method. It is going to under predict. Okay, that I am not showing, it is you just take it as an assignment and do it by yourself. Okay. The next problem that we are going to solve is a problem of a mixture of two solutes. It is basically a fractionation problem. Till now we have talked about a separation and concentration problem. Now we are talking about a fractionation problem. A mixture of two solutes A and B they are subjected to osmotic pressure controlled laminar cross flow nanofiltration. Subjected to osmotic pressure controlled laminar cross flow nanofiltration. Okay. Solute A is completely retained and solute B is partially retained by the membrane. A completely retained by the membrane. And the whole system is at a steady state, and B is partially retained. That means real retention for the component A will be equal to 1, real retention of component for the component B will be something, okay, which is not equal to 1. So, it is given it is the feed mixtures. Let us look into the feed composition. 10 ppm of A and B each. So, 10 milligram per liter of A and 10 ppm means milligram per liter, 10 milligram per liter of B. That is the feed composition. The average cross flow velocity in the channel, it is given that u naught is 0.3 meter per second. If the flow rate is given and the channel dimensions are given, you can also find it out. Okay. Flow rate divided by the cross sectional area normal to the direction of the flow. So, in this particular problem it is given as 0.3 meter per second. So, you can back calculate and find out what is the flow rate from here. The channel geometry is given. Channel geometry or dimension. The dimension is 30 centimeter, 5 centimeter cross 0.15 centimeter. This is the length 0.3 meter, this is the width 0.05 meter and this is the height 0.15 meter. Okay. The membrane permeability is given, it is 2 into 10 to the power minus 11 Newton second per meter cube. That is the typical order of magnitude of any nanofiltration membrane. The real retention of membrane for solute B is given as 0.8 and that for solute A is equal to 1 because it is completely retained by the membrane. Delta P is given as 300 kilopascal, that is the operating transmembrane pressure drop. We use film theory is valid. Although we have seen several shortcomings of film theory, we will be doing film theory during our calculation because it is easier to demonstrate how to calculate the problem. Okay. And just now we have seen one example which we use the 2-dimensional model and the using the shortcut method. Osmotic pressure of the solution for the component A of the solution is varying as 6000 times Ca and pi of B is 6000 Cb. where pi is in Pascal, both pi is in Pascal and C is in kg per meter cube. That means milligram per liter has to be converted into kg per meter cube. Okay. Diffusivity of the two solutes are given. Diffusivity of A is given as 2 into 10 to the power minus 10 meter square per second. Diffusivity of B is twice of that, 4 into 10 to the power minus 10 meter square per second. Solution viscosity and density are taken to be same that of water. Okay. So, if you look into the diffusivity of these solutes, the diffusivity of these solutes are in the order of 10 to the power minus 10 meter square per second. Diffusivity of protein will be in the order of 10 to the minus 11 meter square per second, and the salts will be having the maximum diffusivity in the order of 10 to the minus 9 meter square per second. The sodium chloride will be having a diffusivity of 1.5 into 10 to the minus 9 meter square per second. So, therefore, we are talking about some solutes which will be having a diffusivity in the order of 10 to the minus 10 per meter square per second. That means, these solutes are typically dyes. Okay, those will be having a molecular weight in the range of 400, 500, 600, 700 in that range. Okay. And nanofiltration is typically used to separate these type of solutes. So, solution, let us look into the solution. Ca naught is equal to 10 into 10 to the power minus 3 kg per meter cube. So, it will be 10 to the power minus 2 kg per meter cube, and that is same as Cb naught, right. Both are 10 ppm each. So, U naught is given as 0.3 meter per second. D equivalent diameter is 4 into half height. So, the dimension that was given in the channel dimension, that was half height. Okay. So, this is 4 into half height, H was 4 into half height. So, this turns out to be 3 into 10 to the power minus 3 meter. Length was given as 30 centimeter. So, 0.3 meter. LP was given as 2 into 10 to the power minus 11 Newton second per meter cube. RRB 0.8, RRA 1, delta P 300 kilopascal. Diffusivity of A is given as 2 into 10 to the minus 10 meter squares per second. Diffusivity of B is 2 times that of diffusivity of A, and pi A is 6000 Ca and pi B 6000 Cb. Now, what we can do? We can do a solute mass balance over the membrane surface, and exactly whatever the same way we have done we have derived the film theory equation. If you remember how we did the film theory equation, we derived the film theory equation once we did a solute mass balance over a differential element over the membrane surface and integrated across the boundary layer thickness, because the boundary layer thickness will be constant for a stagnant boundary layer film. Okay. Now, in this case we will do a solute balance, solute A balance over the same element and solute B balance over the same element. Okay. So, if you do that, what you will be getting? You will be getting two different solutions, two different equations corresponding to solute number A and another one corresponding to solute number B, but the permeate flux will be remaining same, that is independent, the solvent flux will be independent of the solutes. So, if you do a separate solute balance, solute A balance over the mass transfer near the membrane surface, you will be getting J is equal to K time K A ln C m A minus C p A divided by C naught A minus C p A. Okay. This mass transfer coefficient will be now will be having the property of solute A, because it is a solute balance of dA by delta. Okay. And all these concentrations will be corresponding to solute A. Okay. Solute B balance will lead you J is equal to Kb ln Cmb minus Cpb divided by C naught B minus Cpb, okay, at the steady state. And one it is given that Cpa is equal to 0 because real retention is equal to 1. So, in the permeate there is no concentration of solute A. If it is instead of real retention 1, if it would have been something else, that would have been put it here. Okay. So, for the sake of simplicity, we have assumed that real retention for component A is equal to 0. So, the permeate will be basically you will be having only one component, that will be component B. Okay. So, we write one equation J is equal to K A ln C M A minus C P A C A naught minus C P A is equal to K times B ln C M B minus C P B divided by C B naught minus C P B, and we have C P A is equal to 0 because real retention of A is equal to 1. Okay. So, you will be having J K A ln C M A divided by C A naught is equal to K B C M B minus C P B C B naught minus C P B, and K will be, since it is a laminar flow, the Sherwood number will be 1.85 Reynolds Smith d by L raised to the power 1 upon 3. We will be using that equation, and for K A and K B we will just put the values of diffusivity or solute properties corresponding to A or corresponding to B. So, therefore, from this K becomes 1.85 U0 d square divided by d equivalent times length raised to the power 1 upon 3. So, K A, if we put the value of diffusivity here for the solute A, we will be getting the mass transfer coefficient corresponding to A. If you put the value of diffusivity of solute B, we will be getting the mass transfer coefficient corresponding to solute B. So, K A will be 1.85 0.3 into 4 into 10 to the power minus 20 divided by 3 into 10 to the power minus 3 into 0.3 raised to the power 1 upon 3, and this turns out to be 4.39 into 10 to the power minus 6 meter per second. Okay. Similarly, we put the value of diffusivity corresponding to the solute B there, and we will be able to calculate the mass transfer coefficient of the solute B. So, just putting the value of that there, and it turns out to be K B becomes 6.96 into 10 to the minus 6 meter per second. Okay. So, now we put these values in the equation. So, you are getting an equation. So, we just equate this equation, this equal to this. So, if you do that, what you will be getting is 4.387 into 10 to the power minus 6 ln of C M A divided by 10 to the power minus 2, that is the concentration of A in the feed, equal to 6.96 into 10 to the power minus 6 log of 0.8 C M B. We are replacing in terms of real retention C P in terms of real retention of B and C M of B, 10 to the power minus 2 minus 0.2 times C M B. Okay. So, in short, this will lead to an equation something this log 100 times C M A is equal to 1.586 log of 80 C M B divided by 1 minus 20 C M B. So, we have 3 equations basically, 3 unknowns here, C M A, C M B and J. There are 3 unknowns in this particular problem. So, one equation is that, the second equation you will be getting is, that is the Darcy's law for the solvent flux. Flux or osmotic pressure model, what is that? J is equal to L P times delta P minus delta pi. Okay. Now, this is a mixture of the dilute solution. So, delta pi should be delta pi should be pi at the membrane surface, osmotic pressure on the membrane surface minus osmotic pressure on the permeate stream, but this osmotic pressure will be the osmotic pressure of the mixture, and since it is a dilute solution in the order of 20 milligram per liter ppm level. So, osmotic pressure of the mixture can be considered as a simple superposition of the osmotic pressure of individual component, okay, pi of A plus pi of B. If you really do that, then what you will be getting is J is equal to L p times delta p minus delta pi, where delta pi will be pi of A on the membrane surface plus pi of B on the membrane surface minus pi of A on the permeate stream minus pi of B on the permeate stream. Now, this will be 6000 times CMA, this will be 6000 plus into CMB, CAP will be equal to 0. So, that will not be there, you will be getting 6000 CPB. This will be 0 because it is real retention equal to completely is equal to 1. So, this becomes 6000 CMA plus 6000 times CMB minus CPB, right, and this will be nothing but real retention of B multiplied by CMB. Okay, so, it is 0.8 multiplied by CMB. So, you will be getting J is equal to LP times del P minus 6000 CMA minus 6000 RRB CMB. So, just put the values 2 into 10 to the minus 11, 3 into 10 to the 5 minus 6000 CMA minus 4800 CMB. Just take 3 into 10 to the 5 outside. So, this becomes 6 into 10 to the power minus 6, 1 minus 0.02 CMA minus 0.016 CMB. So, this is the second equations, and the third equation you will be getting J is equal to Ka ln CMA divided by Ca naught. Okay. So, this is the third equation. So, 3 unknowns J, CMA, CMB, and you will be getting 3 equations. So, 3 equations, 3 unknown system. So, therefore, it is a completely defined problem, and one can get the solution. So, you just use this relationship. So, there are several ways one can do. So, you can use J is equal to Ka ln CMA times Ca naught to Lp into del p minus delta pi. If you do that, you will be getting this expression ln 100 times CMA is equal to 1.37 into 1 minus 0.02 CMA minus 0.016 CMB. So, this gives a relationship between the CMA and CMB, and no, you can. So, basically there are 3 equations and 3 unknown, and one can do an iterative method, because they are nonlinear of solution. 3 algebraic equations nonlinear and 3 unknowns. Okay, this can be solved, and upon solution. Okay, I have solved it in a particular way, you can solve it in another way. So, there are several ways, right, 3 equations, 3 unknown, that can be solved, and CMA turns out to be 0.039 kg per meter cube, and this 39 ppm, right. CMB will be 0.0187, 18.7 ppm kg per meter cube. If you multiply kg per meter cube by 1000, you will be getting milligram per liter or ppm. So, in permeate, CPA turns out to be 1.496 ppm or 1.496 into 10 to the minus 3 kg per meter cube. Okay. And the value of permeate flux J turns out to be around 6 into 10 to the power minus 6 meter cube per meter square second. So, this is the typical problem we have solved, where there are two components present. This is a case of fractionation. Previously, we have solved for a case of separation and concentration. Another case we have solved for a case of concentration in case of batch ultrafiltration mode. Now, this is a particular problem that we have solved for the case of fractionation, and one can really get the system performance by looking into the solution. Now, next problem that we are going to solve is again a gel layer controlling filtration. But in this case, the typical, what is the difference between this problem and the previous problem is that in this case the gel layer is a function of delta P. Gel layer thickness or gel layer resistance is a function of delta P. What does that mean? That means if you increase the transmembrane pressure drop, the gel becomes compact. Okay. So, if the gel layer resistance is independent of delta P, that means it is incompressible. The gel layer is incompressible. If it is a slow function of delta P, then it becomes compressible. So, you will be getting a slight modifications or variation of the transmembrane of the permeate flux with operating pressure. Okay. So, one can find what is the optimum operating conditions or optimum transmembrane pressure drop one has to apply in case of a gel controlling filtration. So, in this case we assume that specific gel layer resistance is a function of delta P. Rg is, if you remember, Rg is nothing but alpha into 1 minus epsilon g rho g times L, where alpha is the specific gel layer thickness, gel layer resistance. The specific gel layer resistance is a function of transmembrane pressure drop, and that functional form is given as alpha is equal to alpha naught delta P raised to the power 0.3. How you will determine this relationship? If you remember, when we discussed about the gel controlling filtration in a unstirred batch cell, you have to plot 1 by j square versus time, something like that, right. Then they will yield a straight line. From the slope of the straight line, we would calculate the specific gel layer resistance. If you conduct the experiment with 3 different or 4 different pressures, you will be getting the corresponding gel layer specific gel layer resistance corresponding to 4 delta P or 4 pressures. Then if you plot alpha versus delta P, that will be typically, this will typically result a curve something like this with a diminishing slope. Diminishing slope means your exponent should be less than 1. If the exponent is greater than 1, then the nature of the curve would have been something like this, but typically we will be getting this. That means at higher pressure, what this curve signifies, at higher pressure it is independent of delta P, that means the gel becomes totally incompressible. So, at lower pressure it becomes compressible. Okay. So, that is how you will be getting this relationship or establishing this relationship by conducting batch experiment under various operating pressure drop. Okay. Now, here alpha is in meter per kg, that is the unit of alpha. Alpha naught is given as 2.56 into 10 to the power 16, okay, in appropriate unit, and delta P will be is in Pascal. Okay. And gel layer thickness is found out to be varying as a function of different function of delta P, and it is established as L is equal to L naught delta P into 0.8. How you obtain this? You can obtain this thing by microscopic observation. That means, after the experiment, dry out the solution whatever is depositing over the membrane surface, put under a microscope and measure the thickness. Then do a back calculation and check how much volume was there in it previously, because it was in the solution, it was in the in a gel state. Okay, so one can back calculate and really find out what is the actual length thickness of the gel layer under the solution, under the wet condition. Okay. Suppose you conduct the experiments at different delta p and found out the relationship between L and delta p is something like this, where L0 is given as 5.74 into 10 to the power minus 11 and delta p is again in Pascal in this correlation. Okay. The gel density is given as 1050 kg per meter cube, okay, and gel layer porosity is given as 0.7, okay, and membrane permeability is given as 5 into 10 to the power minus 11 meter by Pascal second. Okay. Now, what is our aim in this particular problem? We have to find out the limiting operating pressure and optimum operating pressure. Operating pressure delta p is how much, and what are the corresponding value of the permeate flux at this delta p, what is the corresponding value of the permeate flux and gel layer resistance. Okay. So, basically now what we have to do, we have to write down the phenomenological equation. What is the phenomenological equation? That J was driving force divided by the resistances. So, delta p divided by mu times R m plus R g. This is the driving force delta p, mu is the viscosity of the permeating solution, this is the membrane resistance, this is the gel layer resistance. Okay. And membrane resistance we know it is 1 over mu times L p. Permeability multiplied by the viscosity of the permeating solution, inverse of that will give you the resistance of hydraulic resistance of the membrane. Now, what is R g? If you remember the definition of R g, alpha into 1 minus epsilon g rho g times L. Alpha is the specific gel layer resistance, epsilon g is gel density, gel porosity, this is gel layer density, L is the gel layer thickness. Okay. Now, you put different values of expression of alpha as a function of delta p and L as a function of delta p in this equation. So, what you will be getting is that R g is equal to alpha naught delta p raised to the power 0.3 into 1 minus epsilon g rho g times L naught delta p raised to the power 0.8, and just put different values, whatever the different values are given, etc. This turns out to be 4.36 into 10 to the power 8 times delta p raised to the power 1.1. Okay, put all the values together, and therefore, one can get in this form R g is equal to R g naught into delta p raised to the power 1.1, where R g naught is nothing but 4.36 into 10 to the power 8. Now, you put this expression of R g, which is a function of nothing but delta p, in the governing equation of permeate flux, that is delta p is divided by mu R m plus R g naught delta p raised to the power 1.1. Okay. So, in this expression, the permeate flux is a sole function of delta p, all the other parameters are known, and we are going to find out what is the optimum delta p or the limiting delta p. So, I differentiate this equation with respect to delta p and put it to equal to 0. Okay. So, dj d delta p, if you do that, what you will be getting is, we put dj, we evaluate dj d delta p and put it to equal to 0, and this turns out to be 1 over mu r m plus r g naught delta p raised to the power 1.1 minus delta p r g naught 1.1 delta p raised to the power 0.1 divided by mu r m plus r g naught delta p raised to the power 1.1 square of that will be equal to 0. Okay. So, just take the derivative of this with respect to delta p and put it equal to 0, you will be getting some expression, and that expression will be r m after simplification plus r g naught delta p raised to the power 1.1 will be equal to 1.1 r g naught delta p raised to the power 1.1, and it turns out to be r m is equal to 0.1 r g naught delta p raised to the power 1.1, and delta p raised to the power 1.1 becomes 10 times r m by r g, okay, and delta p should be 10 r m by r g raised to the power 1 by 1.1. Okay. So, this becomes 10 by 11. Okay. Let us evaluate that, it turns out to be 0.91, this exponent turns out to be 0.91, and delta p will be around 8.876 into 10 to the power 6 Pascal, and in kilopascal it turns out to be 8876 kilopascal. Okay. So, it is extremely high. That means, if you plot j versus delta p, if you really plot j versus delta p, the plot will go something like this, and the pressure independent zone where the gel layer will be almost incompressible, that will occur at a very high delta p. Okay. That will be around divided by 101, this turns out to be around 88 atmosphere. So, about a pressure of about 88 atmosphere, this particular gel layer, which will be function, this given function of delta p, gel layer thickness and the gel layer resistance, that will be incompressible, will be independent of delta p when your operating pressure will be extremely high. At that limiting pressure, this is the limiting pressure, and at that limiting pressure, the permeate, if you put the value of this pressure, the permeate flux turns out to be 4.41 into 10 to the power minus 6 meter per second, and R g turns out to be 2 into 10 to the power 16 meter inverse. So, naturally one can ask why I should do this exercise, because at that high delta p, which is almost difficult to realize in an experimental condition. If you like to have an operating pressure of around 90 atmosphere, that will be extremely difficult. No, there is every possibility of having an accident. So, why should I do this calculation? We do this calculation because the permeate flux beyond this particular pressure, the permeate flux becomes constant. So, we plot j versus delta p, we conduct the experiments at lower pressure and see that whether this value becomes 4. This will actually, this plot becomes very weak function of delta p. So, if we say that the flux will be that we are getting around 4 into 10 to the power minus 6 meter cube per meter square second at a pressure delta p 10 atmosphere. That means, if I increase the delta p now, I will not be getting much improvement in my permeate flux, because my limiting flux will be 90 atmosphere, but at the 90 atmosphere I will be getting a flux of 4.41 into 10 to the minus 6. So, there is not much gain in increasing the pressure. So, I should not increase the energy cost in order to attain a higher productivity of the system. So, I should operate better to operate at lower operating pressure at 8 or 10 atmosphere in order to get almost same amount of permeate flux or productivity of the system. So, that is why this limiting calculation one should do before identifying what will be the operating delta P that you are going to have in your system. Okay. Okay, we stop here, and in the next class we will be doing some more problems on module design and dialysis. Okay. Then we move on to the next topic. Thank you.